Hi, welcome back. In this lecture, I want to describe the basic concepts of the HHL algorithm, that is a quantum technique that we're going to use for solving a linear system. The HHL algorithm is a quite advanced and complex algorithm, and therefore I'm not going to cover in this lecture all the details. It turns out that exist different implementation. I can refer you to the details of implementation in the textbook, but also you will have a chance to go through the implementation of HHL algorithm for the assignment. So let's give a start. So the basic concepts of HHL is that the solution of the linear system goes through a process called eigendecomposition. If the linear system that we want to solve is AX equal to B, and we want to find the x vector, what we are going to do is to express a to the minus 1 in terms of eigenvalues and eigenvectors of the matrix A. So this is called eigendecomposition. So in fact, any matrix has an associated set of eigenvectors and eigenvalues. This is not something new. So eigenvectors and eigenvalues are essentially the matrix equivalent of the eigenstate and eigenphases of a QPU operation we saw in the quantum phase estimation. So nothing particularly new. We saw that any QPU register can be some superposition of eigenstate of any QPU operation. And we saw that through its dependence on quantum simulation, that is encoding technique for a matrix using the quantum state, HHL is restricted to solving system or linear equation that represented a matrix A, which are Hermitian matrices. Well, we also saw that we can go from any generic matrix, which is not Hermitian, to a Hermitian matrix by using a certain machinery described in the quantum simulation approach. An important aspect that we're going to discuss now is that any vector, so any given vector, we might want to act in Hermitian matrix A on can be expressed on the basis of A's eigenvectors. So the typical example, if for instance we have A minus 1, and then we might want to act to the vector B, and we can express the vector B in the basis of the A's eigenvector. Right. So remember, this is basically the solution of our system AX. So any generic vector can be expressed using the basis of the A's eigenvector. Let's see here an example to make it clear. So we have our linear system that is described by a matrix that is in this case Hermitian. You see here Hermitian, and then we have a vector z 1 and 0. And what you want to do, we want to express this vector z using the eigenvectors and eigenvalues of the matrix A. So the first step is to calculate the eigenvectors. So this is a 2 by 2 matrix, and so there will be two eigenvectors. We can calculate analytically. Also, we can use MATLAB, Python, or Octave in order to calculate the eigenvector. These are the two eigenvectors, V1 and V2. And the associated eigenvalues are lambda 1 and lambda 2. Since A is Hermitian, the vector z can be written in the basis of its eigenvectors, and in fact is easy to show that minus 0.788 multiplied by this vector here, minus 0.615 multiplied by this vector here, is just to give our vector 1 and 0. So what we did, we express our vector z in terms of v1 and v2, which are the eigenvector of the matrix A, resulting from the eigendecomposition of our matrix. So we can also write A in its own eigenbasis when using the eigenbasis to formulate a matrix is always diagonal, and that's beautiful, right? So a diagonal matrix means that its main diagonal consists of its eigenvalues, and off diagonal is everything 0. So we can write A in terms of eigenbasis. So on the diagonal we have lambda 1, and this is lambda 2, and then we have 0. So this is particularly beautiful, the fact that in the eigendecomposition of A, we express A, we can express A as a diagonal matrix. And why this is beautiful? Well, this is beautiful because diagonal matrices are very easy to invert, right? So inverting a diagonal matrix is quite trivial. And that's what the HHL quantum algorithm is based on, right? So we are going to determine these eigenvalues. So we saw before how to calculate the eigenphases with the QPO. So it's not a mystery that we're going to use the QPE, so the quantum phase estimation, and then we are going to create a diagonal matrix, which is quite easy to invert. So as I said, in order to invert the matrix on the eigenbase of A is very easy, and basically this corresponds to take the inverse of the eigenvalue. So you see here we take 1 over lambda 1 and 1 over lambda 2. So this gives us A to the minus 1, so the inverse of A expressed in the eigenbasis of A. We can either leave the inverse like this if we wish to act on vectors that are also expressed in the A eigenbasis, or rewrite in the original basis. Basically, then we need to operate bringing back the eigenvectors of the problem to move it back to the original basis. What we're going to do in this particular case, we're going to use the vector, in this case is the source, using the eigenbasis of A. So we can express the solution of our problem as a matrix multiplication of A to the minus 1, which has on the diagonal all the reciprocal of the eigenvalues of the original matrix A, and the rest is 0. All right, so we have just a matrix, and then we are having the vector B expressed in the eigenbasis of A. So once we have these two things, it's quite easy to calculate the unknown. And this is the principle the HHL algorithm is based on. So this is the implementation, the quantum circuit that the textbook is presenting. I'm not to describe it into detail, I refer you to the textbook, but you see here a different part. So we have a first important part, and it is the phase estimation, and this is going to be responsible for providing our eigenvalues, right? Lambda 1, lambda 3, depending on the size of our problem. You see here, you probably remember in the QPE, we have the eigenstate. Instead of the eigenstate, we provided source terms B that has been encoded using the amplitude encoding. And this is our output register in the phase estimation. After this, we're going to have the eigenvalues, and we need to do one operation. Remember that we want to invert. At this point, we know that lambda 1, lambda 2, so forth, so on, are going to be the elements on the diagonal. What we need to do is to take the inverse and to encode it in the amplitude of the quantum state that we are studying. So we might have a different kind of machinery to invert. So it means that we go from lambda 1 to 1 over lambda 1, 1 over lambda 2, and so forth and so on. And then at the end, we have a non-compute part to basically disentangle the quantum register, so to allow additional operation. At the end of this algorithm, the output register from HHL will contain an amplitude encoding of precisely of the vector where the amplitude of state I is described by B divided by lambda I. That is the actual solution. So this, remember, this is simply the solution of xi. You see here. So this is just a brief overview with the main concepts of the HHL algorithm. I'll let you study or go deeper if you want to, reading the textbook, or also attempt and develop an HHL algorithm in the assignment. Talk to you soon.